which is the ideal class group of this field. Finite extension is Galois group is isomorphic to Cn. And now, as I say, it's a fact that Wn is actually a point on E with coordinates in h of n. And so the natural thing is to take its trace on the elliptic curve, and so that will be the definition of the point u of n, which will be its trace from h of n down to the field k of n of Wn. So this is the Hager point we're interested in. Now the whole problem now, and this is where in some sense the classical theory stops, is that the big question is this point a finite order or not? And the whole problem is that the only way we know that it is finite order with our knowledge up so far is if the complex L function, L-E-N-S, has a simple zero. And s equals 1. That's what the existing theory would tell us. But the problem is we don't know how to prove that it has a simple zero s equals 1. And we simply don't know, or we didn't know before Tian, how to in fact, what we're going to do is one's going to use an argument involving this Hager point and various other facts about L functions to conclude this eventually. Whereas up until now, one would have said, okay, we try and prove this analytically, but the analytic people don't know how to prove it. That's the problem for such families. Okay, so now one further word. That let me right now, just because you see I'm now going to be describing Tian's induction argument, so let me write my n, it will be minus P naught times P1 up to Pk, where Pi for 1 less than or equal to I less than or equal to K splits completely in the field Q adjoint E4. So that's what n is, and now by Gauss's theory of genera, you in fact see that there's a subfield here I'm going to call Jn that will play a crucial role, and it's the field that you get by adjoining to Kn the square root of minus P naught and the square root of P1 plus P1 up to Pk. In fact, it's rather easy to see that that has to be a subfield. It's an unramified Armenian extension. What's not quite so obvious is that this Galois group here, which is a subgroup of Gn, is precisely twice the ideal class group. And therefore, that extension, eventually we'll need that, and this extension will have odd degree precisely when the ideal class group has no element of order 4. Now, one other remark that I'm going to, we're looking at the points in EKN, and I'm most interested in the points that I'll call the subgroup, which I'll call EKN minus. And by definition, this is the set of all points P in EKN such that tau of P is minus P, where tau is the non-trivial element of the Galois group of Kn over Q. So in fact, these are precisely, you can identify these points with En of Q, and that's where we want eventually construct it. Okay, so now the crucial idea of Kian's work is the induction method, and let me say what it proves in this case. And then I want to talk about the ideas moving through. So the actual theorem that one proves is the following, that assumes K is greater than or equal to 1. The case when K was lower is in fact classical. It was done by Birch long ago. Then, in fact, UN always belongs to 2 to the K minus 1 E of Kn minus plus E of Kn. This is the crucial step, which is really new, because as we'll see, I'm going to say a word at the end, but once you have this statement, you can in fact use the same argument as essentially, it's a little more work, as used by Hagener and later Birch in special cases when K is 0, to conclude the theorem. The crucial thing is to be able to show that this Hagener point lies in this, as K gets large, this very large multiple of EK minus, and you don't care about Q. Now, the very ingenious method that Tian has for doing that is to use an induction on K involving imprimitive Hagener points. They've always been there, these imprimitive Hagener points, but I think no one found any good use for them before. So let me quickly recall the definition and the key fact that emerges. So now let me define D of n will be the set of all negative divisors. So negative divisors of n, which are divisible by P naught. So you see, if you take an n dashed in D of n, we will again, it will have root number WE of n dashed, will again have root number minus 1. It will be exactly one of the ones that we're looking at with a smaller set of primes involved. But now, if n is dashed is not equal to n, we can do the following. We can let chi n dashed be the character of the quadratic extension Kn adjoin the square root of n dashed over Kn. Now you see, because this field here, Kn adjoin the square root of n dashed, will again be just a quadratic subfield of Jn. And so it lies inside the Hilbert class field, and so therefore we can make the following definition of the imprimitive Hagener point. Un n dashed will be the sum of the sigma in Gn of chi n dashed of sigma, sigma of Wn. So in fact, this, if I took chi n dash to be the trivial character when n dash is n, you see we again would have the new n, which would be simply my original Hager point Un. And now here's the first key use of, that I now want to explain, of L values. I'm trying to prove that here. So if I have any n belonging to the set P of E, so now this is an M where the root number is +1, let me define its algebraic L value of EM1 to be L EM1 times the square root of n over the same omega infinity, the same real period of E as before. So this factor of square root of n here is just, it's the change in the period when you twist the curve. And then also let me write h hat for the canonical Néron-Tate height on Q bar, the absolute Néron-Tate height. And then the key fact that you prove is the following theorem. And I just have to state it, and then it's the proof depends on the front. You apply the Rose-Sardier and Polyvariant theorem, which are partial results in the direction of the Berg-Swinnerton-Dyer conjecture. And so you get the following result, that assume that this Hager point, Nn prime, is not torsion. If it is torsion, it turns out it's absolutely harmless. But let's assume it's not a torsion point. Then Un dash, which would be the Hager point that I defined for n, but for n dash, is not torsion. E of Kn dash has rank 1. And the crucial thing is that you can compare the height, the canonical height, h hat of U and n dashed over h hat of Un is given by the following ratio of L values, namely its L algebraic En. I'm sorry, En over n dashed. 1 over L algebraic of E1. So now these L values here, this is the heart of the method, are L values where the root number is +1. And we know, in fact, that because we assume that U of n dash is not torsion, that these L values are not 0. So if you knew that there was a large power of 2 dividing this is a rational number, these L values, this would tell you that the height of Un dash, this should be Un dash here, is much larger than the height of the primitive Hager point Un dash. Now, in fact, that's exactly what, and I stress here that this, you see, n over n dash belongs to the set P of E. The twist where the root number is plus 1. So in fact, there you can, let's go back to that now. Now, if we knew the exact formula of Coates-23 diagram for this twist, E of n over n dash, there would be nothing more. I mean, I can just cite a result now. But in fact, and all we would need to know is the two-part of the Coates-23 diagram formula. But it's completely unknown. I mean, there's a lot of loose talk in the literature where people say that the conjecture of Coates-23 diagram is proven for a set of curves with positive density. It's complete nonsense. The exact formula is, in particular, the two-part of it, is known for very, very few elliptic curves. And what we need to complete this proof is precisely that two-part. And we still don't know how to prove it, but at least one can prove the following weak form of it, which is all we need. So assume that n does belong to this set P of E. And L EM1 is not naught. If it's 0, we don't care, because then my point would be torsion. Then the order of 2 of this rational number, L algebraic EM1, is greater than or equal to 2 of Kn, where I've now written n as a product P1 up to P, say, of Kn. It's the number of prime factors of K of n. And by the way, again, this is where we need that the two primary part of SHA for this twist is non-trivial, because if the two primary part of SHA was trivial, the conjecture of Birch's-Whitman diagram would tell us we get 2Kn minus 1 here. And the argument would not work. So there are very mysterious things going on here. But now, you see, it's this 2Km which will... So let me write down now one last, not very difficult averaging lemma. And then you will see so the averaging lemma is the following proposition, and again it's just proven by looking at the behavior of the Hagen points under the action of Galois, then assume K, let me write it K of n if you like, because it depends on n, is greater than or equal to 1, then in fact the sum over all the n primes in D of n of u n n dashed is 2 to the kn times v of n. So, excuse me, this is in here, where v of n is the trace from Hn now down to J of n of the Hagen point upstairs W. So you have this rather easy averaging lemma. If you add up all these imprimitive Hagen points, you get 2 to the Kn times another point. And you see, by induction now, if you put these two weak forms of Birch-Swinnerton diagram together, you can then show that that all the n, not n dash not equal to n, lie in 2 to the kn v of n. 2 to the kn times the Mordell-Weil group of the appropriate field. And therefore, the remaining point, remember UN is UN. It will be divisible by 2 to the kn. But that divisibility takes place in the field E of Jn. So when you pull it, you have to pull it down to E of Kn, and so you lose one power of 2. So this is Jiang's beautiful argument. And it goes through, these are the sorts of ingredients here, and of course you could vary the method a little, but basically this is what one would need, something of this kind for any elliptic curve. So the final step, let me just say a word about that. Is the following, that so now we know that we have shown that U of n is in 2 to the k minus 1 E of Kn minus plus the torsion part. And that's without any hypothesis on it. And I should say that, something is needed here to finish off the proof, because there must be lots of n for which the L function has a triple zero, say, with this hypothesis. So that we couldn't expect to be able to show, for some n, there really are triple zeros, or 5 zeros more than 5. So now, if what you show is that if the degree of Hn over Jn is odd, if that degree is odd, then, again by a simple argument which essentially goes back to Hagen and Birch, but it's a little more complicated here, you show that UN cannot belong to 2 to the k times E of Kn minus plus E of Kn torsion, because you see straight away that you get a simple contradiction if it does belong there. Again, using this statement here. So in particular, this implies certainly that UN is not torsion. And that completes the proof. Now let me just say that we are trying at the moment to extend this. It looks as though, so one would, in fact, every elliptic curve with complex multiplication, defined over Q, with complex multiplication by Q of the square root minus 7, is isogenous to a twist of this curve. And so if one wanted to prove analogous results for all elliptic curves within this family of the ones with complex multiplication, are the ones with good ordinary reduction of 2. If they have good reduction of 2, one has to look at other twists and then start taking twists of them. And we do have, I won't say any results now, we do have, I think we have half the proof for an interesting infinite family of twists like that. But even there are interesting new problems which seem to arise. In any case, let me end here. I hope I've given you some idea of the sort of techniques he uses and what one has to look for if one wants to generate. Thanks.
thank Professor Coates for a beautiful talk. Are there any questions? Any questions? Yeah.
Well, the congruent number problem is you see, the n is congruent. N is congruent. If and only, this is an ancient lemma, goes back to, if and only if the curve, if you take y squared equals x cubed minus n squared x, has a point of infinite order, has g of the n greater than or equal to 1. So it's all a question of producing a point of infinite order. To show n is congruent, we have to produce a point of infinite order on this curve. And this is what, the old timers, the really old timers, simply wrote down points. And Heidner was apart from a sort of certain families kind of parameterization, but they're not so important. But Heidner was the first person to show that when n is a prime, congruent to 5, 6, or 7 mod 8, well, twice a prime, so 6, then in fact there always is a point of infinite order. And he didn't quite write down this Heidner point here, but essentially that, to show it was infinite order. And this is the, you see, the other mystery in the congruent number problem is that in fact the L function of this curve has Wen equals -1, precisely when n is congruent to 5, 6, or 7 mod 8. So for those n, it should always be congruent. And that's, now I'm sure Tian is probably going to mention the most up-to-date results of that in his lecture tomorrow. But it's still, they've made enormous progress on that, but it's still, we're still a long way from proving what Birch and Swinnerton and I predict. This is certainly one of the major problems in number theory. Show that every integer in the residue classes of 5, 6, or 7 mod 8 is a congruent number.
So for the family of targeting twisting of these curves, do you see that unique phenomenon?
Right, probably, of course, depends on your outlook, but probably everything in one family of quadratic twists of a fixed curve, probably every known arithmetic phenomenon will happen. We can't prove. If the rank of the Mordell-Way group gets arbitrarily large, which we don't know, presumably it happens in such a family. I think it's fair to say that in one such family, probably everything. I will not go in and do it.
Probably, yeah. But every family has always been behavior.
What's the idea of the problem?
This one.
Yes.
Wow.
So what's the idea? How this congruent is possible?
Well, I forget I don't ask you to represent, but the central thing is you can write down from a triangle, you can write down a point, and vice versa. Because a trivial is disappointing. So mathematics. Well, you see, I think, again, the literature is so discard, but in some sense, I think certainly by the time of Fermat, people were aware of these things. Because it's used descent on that curve. That's how it all started. Whether it was learned through